In this video, we'll look at how to utilize seismic design rules in RISA-3D in accordance with AISC 341 and AISC 358 to seismically design a steel frame system. So we can see here that we have the lateral systems of the structure modeled. So I have a few moment frames and then also a brace frame and also a chevron brace frame. I can also go ahead and turn on the diaphragm. So I have 5 rigid diaphragms basically at each level here. So we can get a side view here and see those different levels. Now, having these diaphragms allows us to use the seismic load generator to automatically apply seismic loads to the diaphragms based on the defined code parameters. And so to define loads, I'm going to go ahead and on the Advanced tab here, click on the Seismic Load Generators button. So when I do that, I'm brought into the Seismic Load Generators dialog. And the first thing I can see here is I have a seismic weight load combination. This is just the dead load applied in my structure, so self-weight plus some additional dead load that I've applied. I can go ahead and then select the code. Let's use AISC 716 here. Risk category. I'm also going to set my site parameters, so my S1, SD1, SDS, and the long period. So I'm going to keep these values the way that I want. I can also come in here and look at the structure characteristics. So I can set our CT and our exponent factor. We'll set an R factor, so I'll use an R factor of 8 in this case. We can also establish the information or the factors for the overstrength, so the omega factor here, the CD, so the deflection amplification factor, and also the redundancy factor or rho. Now, when we have the characteristics set up the way that we want, I'm going to go ahead and click Calc Loads. And RISA is just going to go ahead and calculate the seismic loads and also the seismic provisions. Now, when it's complete here, we can see all the generated input based on the inputted characteristics. We can see the period determination based on our CT and our CT exponent here. So we've got our determined period. And then we can also see the seismic generated forces. So at each level, so every place I have a diaphragm, so levels 1 through 5 at different heights, so 10 through 50 feet, we've got a certain weight. Now that's based on the self-weight of our structure, as well as the dead load that I've got applied here, and that comes out of that seismic mass load combination. And then the force at each level. Additionally, we also have that center of gravity. And so with that, we get our total base weight and our total base shear. Now, when we're ready, we can go ahead and generate these loads. So I'll just click the Generate button, and it's going to go ahead and generate our basic load cases from BLC4 and beyond. So if I go ahead and click Generate, we'll just solve this real quick, and it'll generate all our loads. And we'll know right off the bat that it generated our loads. If we go ahead and turn on our loads and then toggle to our earthquake loads, we can go ahead and see those point loads applied at the node in the center of that diaphragm. Now, we can also go ahead and open up the basic load cases, and we can see those loads generated. So here in this case, if I just expand this a little bit, we have the earthquake loads in the Z and the X direction, as well as the eccentric earthquake loads, both plus and minus, in the X and Z direction. And so we can go ahead and actually click on one of these loads and see exactly what that load is. So at node 84A, it's a load applied in the Z direction and it has this magnitude in kips. And so we can see exactly what's being applied by the RISA-3D seismic load generator. I could also go ahead and switch a few of the load cases. So if I want to switch to the Z direction and look at let's look at the X direction, we can see those different loads that are applied on those different levels. And so all of these loads are what's going to be used to apply the lateral load to the diaphragm and then distribute the lateral load based on the rigid diaphragm action to these different frames. Now that I have our seismic design loads set up, we need to set up seismic design rules. And so there's a few different ways to do this. We can first just select a member. So I'll just select any member. In this case, I'm going to select a column. And if I open up our design properties portion of this particular column here, we can see at the very bottom here, there's a setting for seismic design rule. So I have a few different seismic design rules that are pre-established by RISA-3D. I can go ahead and select one. So in this case, I'm going to select a ordinary concentric brace frame. So I can select that. And if I wanted to see all the parameters of that particular seismic design rule, I can go ahead and click on the ellipsis button here to either create a new rule or to edit and view the existing design rule. So that's what we're going to do. We're going to edit or view that. We can see all the properties of this ordinary concentric brace frame. And so we can see what type of moment connections do we want to use, what's our frame ductility, where do we want to require overstrength, and then also if we want to include K over R limits for slenderness for our braces. Now, this is really good when we're looking at really one specific seismic design rule, but let's go ahead and look at and review all the options for seismic design rules in the seismic design rules spreadsheet. So I'm going to go ahead and click OK and just click Escape here, and I'm going to come over to seismic design rules. And so here's our seismic design rules spreadsheet. We can see very plainly that we have a variety of different design rules that are already pre-established for columns, beams, and braces. And so in this case, we can see we have ordinary concentric brace frames. We have specially concentrically braced frames. We have ordinary moment frames, intermediate moment frames, and then we have some special moment frames with reduced beam section or with Kaiser. Now we also have some information about frame ductility that we can set here. So whether it's high, moderate, or minimal. And then finally, whether or not we're going to require overstrength for these particular frames. Now, if you want to know more information about kind of the methodology that's being used or why the frame ductility is set as it is, we can go ahead and just click F1 really quickly. And I'll get opened up the seismic detailing web help section for RISA-3D. So in this case, we can look here to see, okay, what are our options for ductility? So high ductility refers to a frame which requires seismically compact sections, okay? Moderate ductility refers to a frame which requires compact sections for frame members. And then here's our minimal ductility. And then it's some additional notes about kind of what's going on and the comparison between different codes and whatnot. We can also go ahead and look at information about overstrength, how is that applied? And then also how we start to apply information for, say, beams. So if I switch here to the beams tab, we can see, again, we have those same labels, but we have now new sections based on the connection type. So for brace frames, our beam connections are just going to be other or none. But once we get into other types like ordinary moment frame or intermediate moment frame or special moment frame, we have some different types of the connections that we have here. So whether we have a reduced beam section or a bolted flange plate or some of the other types of sections here, we can go ahead and evaluate or add these based on the section type that we want to use. So maybe I want to use a reduced beam section for an ordinary moment frame in this case. And again, if I switch back to our web help, we can go ahead and see the different moment connection types that we have. So bolted, unstiffened, extended end plate connection, welded, unreinforced flange, welded web connection, Kaiser bolted bracket, different connection types based on AISC 358 that are available to use here in RISA-3D. Now we also have the option for whether or not we want to require overstrength for the different beams. In this case, maybe we'll just keep overstrength on for our special concentrically braced frame. We also have the Z factor. That Z factor is used to define the reduction in the plastic hinge moment expected for the reduced beam section. And so usually that value is between 0 and 1. We have here the section about all the information about that in the help here. And then finally, we have our hinge location. So we can set our hinge location along the length of the beam based on how we want to analyze this particular section. Finally, if we go ahead and click on our last tab, which is braces, we can see the basic same information for those labels. We can require overstrength, or the new option here is whether or not we want to limit our slenderness check to KL over R. And so again, for this size, special concentrically braced frame, we're going to go ahead and do that. Now, if I wanted to at any time add my own design rule, I could just go ahead and click enter, and I could set my own design rule for columns, beams, and braces in any way I wanted to. So I didn't have to stick to the rules that RISA had. I could go ahead and add a new rule if I wanted to change something, or if I wanted to modify the ordinary moment frame rule in one part of the model against another part of the model. We can go ahead and do that. In this case, I'm just going to go ahead and delete that row. Now we also have some rules for concrete walls, but in this case, we don't have any concrete in this system, and we can go ahead and review that in a separate video. Now I'm going to go ahead and close our seismic design rules, but now that we've kind of talked through our seismic design rules, we need to go ahead and actually apply those design rules to our model. So I'm going to go back to the Home tab here, and let's turn off the rendering. And I'm just going to go ahead and also turn off the loading, but I want to go ahead and select the different frames and assign the design rule that is appropriate. And so we could obviously select member by member, or in this case, I'm just going to kind of group select this first frame here. And in my properties, it's selected all the elements. So I can go ahead and choose, I want to select all hot rolled steel members. And then coming down to the seismic design rule, I can choose which design rule I want to use. So in this case, let's go ahead and set that as an intermediate moment frame. And then if I hit escape, I'm going to go ahead and turn on the labeling and the coloring for that so I can see this. So let's turn on our seismic design rule and then the coloring for seismic design rule. And then I can come over to our brace frame over here. I already set that one ordinary concentric brace frame. I can go ahead and do the same thing for all those hot rolled members. So let's go ahead and choose the OCBF. I can do the same thing down here, selecting the chevron brace. And let's go ahead and make that a special brace frame. So special brace frame, there we go. And then finally, let's go ahead and select our last option. So let's select our last moment frame here. And again, select all those members and go ahead and do a special moment frame with a reduced beam section. So once those are all applied, we can see both the labels and the coloring. So it's very easy to see exactly what design rules are being used in this case. So, matching very easily to the legend here. So with our design rules set, we can go ahead and create load combinations before we run our analysis. So I'm going to go up to our load combinations. And we have that one load combination already established. That's our seismic weight combination. I'm going to go ahead and click on the LC generator. And let's go ahead and create our load combinations that are required in this case. So in this case, I'm going to first create gravity. I don't want to create any of my deflection combinations. I do have roof live load, so we'll keep that. And then I'm just going to do ASD combinations. So 2018 IBC ASD combination, I'll click generate. And so it generates just 4 combinations here because I have dead live and roof live. Next, I'm going to go ahead and switch to the seismic tab. And using the same 2018 IBC ASD combination set, I'll choose that I want the X and Z seismic load options. And I do have a redundancy of 1.3, so I'll include that. And I do want to include the vertical component here, so I'll include that EV. I also do have an overstrength set, so let's go ahead and turn on X and Z for overstrength as well. And so if I generate all those combinations and then close this out, we can see all the combinations that are generated for us. So we have these 17 combinations, and within the individual basic load cases, we can see the different parameters that are applied to, for instance, the dead load or the seismic load. So in this case, the SDS factor, that's that vertical component applied to the dead load here. The redundancy factor applied to our seismic load in the EX and ELZ directions. Also the omega factor, so we have our omega for our overstrength combinations here, and you can see in the combination itself in the name, you have OS, that's an overstrength combination. And so we can, once we have this all set up, we can actually go ahead and run our analysis. So when I'm ready to solve, I'm going to go ahead and use a batch and an envelope solution. This is going to go ahead and give me the individual load combination solutions as well as the envelope of all the load combinations together. So I'm going to go ahead and click batch and envelope. The solution will start here and it's going to go ahead and run the individual load combinations and then give us the envelope. Now I requested just in my application settings that I'm not requiring P delta even though I ran it, so I'll click OK. And then we get our envelope node reactions. I'm going to go ahead and close that table as well as our load combinations table. And let's go ahead and start to review some results. So the first place to start is probably just our regular code check. So on the Explorer tab here under results, I'm going to go ahead and click code check. And when I'm presented with that spreadsheet, we can go ahead and see the results here. So the code checks here, we can see the failing members over 1, they're in red. I can go ahead and sort this. Sort absolute max to min, and so we're going to get all the failing members here. So we have some of our braces and some of our columns failing in this particular case. Now additionally, what you'll see here in the load combination column here is you'll see a star next to some of the combinations. That denotes that this particular combination is an overstrength combination. So the overstrength factor is being used in the solution here and in the controlling load combination. Now with that, we can go ahead and kind of stop looking at the AISC 36016 code check, and let's go ahead and look at the seismic detailing information. So I'm going to close that spreadsheet out, and let's go ahead and open the seismic detailing spreadsheet. So the seismic detailing spreadsheet has 3 separate tabs. So a tab for columns, a tab for beams, and a tab for braces. And so let's go ahead and look at some of the different information in each one of these tabs. So for the columns here, we can see the different design rule that we set. So that was the design rule that we set for any of the members. Our ductility, the same thing that we set. And then we have our max unity check for that member. Again, we can see the load combination. In this case, most of the overstrength combinations are what's controlling. So combination 14 and combination 15. We can see information about slenderness checks, panel zone checks, and then even a panel zone equation. So exactly kind of what's going on in this particular element. Whether or not we need a continuity plate. And then if we need a plate, what equation's being used. And then also some information about strong column weak beam ratio. And so we can see pass failing, as long as we're over 1, we're getting a passing result here. And then also that strong column weak beam, the actual beam that's being checked there. Now, it's great to look at this information in a table, but what if we want to look at this information in a detailed report? So if I go ahead and click on results, I can always open up a detailed report here, or I can right click on a specific member, in this case M1, and open up the detailed report. And so maybe if I want to look at this detailed report, I can go ahead and make this a bit bigger. So let's go ahead and expand our detailed report so we can see a bit better. And if I zoom down here, we can see the whole section for our envelope seismic detailing results. Now, if I open that section up, for this particular column, we can go ahead and see exactly what's going on. So we have a failure in the flange, so we have a non-slender flange, which is recalling us to fail. And as a result, we also have a panel zone failure for web reinforcement required. And we also need a flange stiffener required for a continuity plate. And so it's telling us exactly kind of what's going on in these particular cases. We can also see from a beam standpoint at beams M7 and M9, the demand that's required, the capacity that we have, and then the unity check for each individual condition, flange bending, web yielding, web crippling, the thickness of the flange, so on and so forth. So we can see all of this information. Finally, we can go ahead and look at our column flange bracing forces. So we can see this information when we have a strong column weak beam setting that's less than 2. We can see these different equations and these different provisions that are implemented based on AISC 34110. Now, all of this information allows us to determine how to best design these individual connections and also either modify our seismic system. Maybe we've just determined that in this case, the special moment frame isn't working, or this tells us that we need to upsize the member, right? We need a larger column in this case. So let's go ahead and close the detail report for the column, and let's go ahead and look at the beams, for instance. So again, more information about the beams, the slenderness check, the max unity check, the ductility required, our required shear and moment, again, our strong column weak beam ratio, and then the corresponding column here. Also, our span of depth ratio that we set here, as well as our miscellaneous checks. And so if we want to go ahead and look at some information here, let's not look at a special moment frame beam. Let's go ahead and look at maybe an intermediate moment frame. So let's go ahead and open up this detailed report. And again, if we scroll all the way down to the bottom here, we can open up the seismic detailing information so we can see some additional information on this beam here. So we can see that this member is seismically compact, so that's good. We can see the column beam ratio, just for reference in this case, 593, so that's okay. We can also see the required moment strength and the required shear strength. So this is information that we could use to design our seismic connections in RISA connection if we wanted to. So all of that information can be useful to you as you design the member and as you proceed into designing the connections. Now, at any time, if we wanted to add this to our report, you can go ahead and click the button up here in the top right-hand corner of the report, say, I want to add this particular one to our full detailed report, and you could then review that along with other information in your detailed report interface. The last thing we're going to look at is braces. So let's go ahead and look at our braces here. So we've got our braces in our ordinary and special brace frame systems. And so if I go ahead and, again, look at the information in the spreadsheet, we can see one of the biggest differences is obviously the slenderness check that's being done, and then the required tension and compression, and then also if there's unbalanced vertical forces and as a result, an unbalanced beam force. And so with that, let's go ahead and look at one of these special concentrically braced frames. So let's go ahead and look at, M66 here, and again, open up the detailed report. And so if we open this detailed report again and scroll down, we can see the information for the brace. So the first thing that kind of pops here is we've got a failure for slenderness. And now remember, back in our seismic design rule, I can open that back up real quick for our brace. We set that slenderness check, that K/R, to be for our special concentrically braced frame. So that check is being implemented here, and we're seeing that, okay, the K/R is 145, and that's greater than what we have, and therefore we're failing in this particular case. And so we would need to do something from a slenderness standpoint to make sure that this brace member, passed that slenderness check. Additionally, we can see the unbalanced forces that are calculated on this beam. So the unbalanced forces that are calculated on the beams in the system, they're really just reported for reference only. And typically these unbalanced forces on the beam are due to the chevron brace configuration. And that's what we have for this specially concentrically braced frame. Now, any of this information, when you're finished viewing it, you can use this to either create a report of this entire project, right? Or you could go ahead and send this information, this connection information specifically, into RISA Connection to design seismically detailed connections. Now, when you're finished reviewing the seismic detailing results, you can either create a report for the entire project using the report printing interface. So you could create some screenshots or send detailed reports or any of the spreadsheets, or you can send all the connection information, including the reactions, as well as the information about the seismic design rules, and even you can set a connection type to RISA Connection to design seismically detailed connections. Now, for more information about seismic design for steel structures in RISA-3D, please visit RISA.com.